A major security challenge with the CAN bus is the lack of authentication. Essentially, any device can join the network without being verified. This creates several vulnerabilities. First, it allows for spoofed messages where devices can pretend to be something they are not, potentially causing the vehicle to behave unexpectedly. Second, unauthorized access becomes easier, enabling attackers to eavesdrop or even inject malicious commands. Third, denial of service attacks become possible where an attacker floods the bus with fake messages, disrupting normal operations. Finally, troubleshooting becomes a nightmare as it's difficult to pinpoint the source of issues when any device can send messages. The lack of authentication also limits the scalability of the CAN bus as managing and securing a growing number of unverified devices becomes increasingly challenging. The lack of encryption is also a significant security vulnerability in the CAN bus. Due to resource limitations in ECUs, implementing robust encryption has been challenging. This opens the door to several threats. First, eavesdropping becomes a serious risk, allowing anyone on the network to access sensitive data like sensor readings and control commands. Second, message tampering becomes possible, where attackers can modify data during transmission, potentially leading to vehicle malfunctions. Third, replay attacks are feasible without encryption. Attackers can capture and replay legitimate messages, tricking the system into performing unintended actions. Finally, the lack of encryption hinders the adoption of future technologies like V2X communication, where secure data exchange is crucial. Another critical security issue with CAN is the lack of sender identification within messages. This means any device can send a message without revealing its identity. This lack of information leads to several problems. First, it creates a vulnerability where malicious actors can spoof messages, pretending to be a legitimate device. This can cause unintended actions in the vehicle, potentially leading to safety hazards. Additionally, it makes troubleshooting difficult as it's challenging to pinpoint the source of a problem. Furthermore, without knowing the sender, it's difficult to hold anyone accountable for a security breach. The CAN bus is a single, shared network where all devices communicate with each other. This lack of segmentation presents several challenges. First, it increases the attack surface. If one device is compromised, the entire network is vulnerable. Also, problems in one part of the network can spread to others, causing cascading failures. Finally, managing and troubleshooting a single, large network with many devices becomes increasingly complex as the network grows. The CAN bus's fault confinement mechanism, while intended to maintain stability, has some limitations. First, the system can be overly aggressive, removing functional nodes due to temporary errors like electrical interference. This disrupts system operation unnecessarily. In addition, a single critical node failure can bring down the entire network, creating a single point of failure. Also, the lack of built-in redundancy means the fault confinement system itself can become a point of failure. The CAN bus's priority-based arbitration system, while useful, presents some security challenges because first, adversaries can use it to create delays for lower priority messages, which is problematic for time-sensitive applications. This can be exacerbated by a constant stream of high-priority messages, potentially causing a denial-of-service situation. Also, the fixed priority system struggles to adapt to dynamic conditions where message importance can change.